Right, hello, welcome, Wave Motion 3. This one is all about superposition and interference. Da, 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 da. Why did it warrant a song? I don't know. It didn't warrant a song. Sorry. Right, okay, so state and apply the principle of superposition. That's the first thing you'll need to do. Define and explain the terms interference, coherence, destructive, constructive, and phase, and path difference. Quite a lot to do. Describe Young's double slit experiment and know and apply the Young's double slit formula and the diffraction grating formula. Quite a lot in this bit, so we'll power through. Right, okay, so superposition is this cool thing that if you've got two waves and they overlap on top of each other, they can add to each other. It basically states this. The principle of superposition of waves states that when two or more waves meet at a point, the resultant displacement, which is the value that it is on the y-axis, is the sum of the displacements of the individual waves. Now that basically means at any given point, the sum adds up, like this. So at this location on the distance axis, wave A has a displacement of 1, wave B has a displacement of 2, and so I bet you can guess what the resultant wave has a displacement of. Right, it's 3. They've just added up, they've summed up like that. So just quickly have a look at this one, and I'd like you to draw those waves out and draw what you think the resultant wave would be based on that. Now, just to be clear, you can see what the resultant wave does. It doesn't just stay at 3 the whole time. It follows the path of the resultant of the sum of these as they change through the distance. So have a go at that and bring that in. Right, this is all because of a property called interference, right? So this is a prime example is with sound. You can observe this with sound. So imagine we got two speakers over here. They're approximately 1 meter apart, and they emit sound. Their cones are pointed directly parallel to one another. What we'll note is that at some points, the waves are what we call in phase with each other. If you remember phase from the phase guy video, it's basically saying that if two waves are in phase, they are doing the same thing at the same time. So when it's up, it's up. When it's down, it's down. Like the Duke of York's men. When they were up, they were up. And when they were down, they were down. That's in phase. So if they're both doing the same thing at the same time, they're going to add to each other. And if they are out of phase or in completely out of phase or in antiphase, they're doing the opposite at the same time, then they will cancel each other out and result in that. Now that's true if they have the same amplitude, obviously. That won't cancel out. If that's 1 and that's 2, the resultant will be -1 or whatever, like it'll vary. The resultant wave will have an amplitude of 1. So you can have places while you move down here where it'll suddenly be loud, and then it'll get quieter and quieter and quieter and eventually be silent, and then be quiet, louder and louder and louder, and be very loud again. Now, because of all the reflections in a room, you don't really often get silence and sudden loudness. But you can observe this in real life. You can observe this a bit in real life. So we define those things as being constructive and destructive interference. So we say constructive is where they are in phase and it results in the gain in amplitude compared to either of the two original waves' amplitudes. And destructive is when the resultant wave is 0. So it's simplistically 0, but all reduced. It's destructive if it's reduced. Completely destructive is when it's gone. So if they're in phase, they are 0 degrees out of phase, or 360 degrees out of phase, or 720 degrees out of phase. So no phase difference. But they're destructive if they're 180 degrees out of phase, or any odd multiple of that. You can see this same thing with water waves. If you get this set up like this with two ball-ended dippers that just go, and they make 2 point disturbances, both those waves will go like that and spread out like you can see. And there are points where they overlap, where it's continually cancelling out or continually adding up, constructively interfering. So you can see the regions, for example, X, where the interfering waves are in phase, and all along point C, you can see, all along line C, you can see that they are constructively interfering, and at these points, the wave will be traveling like a high bit. Along D, it's where you've got opposite waves crossing each other, and they'll continually do that along that line of action, and they'll be destructively moving forward. So it won't be like that moving through. It'll be like a single high bit and a single flat bit moving forward out, and that's because of that interference of those two wave types. You see it with light as well. You see it with any wave, but some examples. Laser shining at some slits. If it was 2 slits, that produces what we would 2 separate sources of light, very close together. And then as they are diffracted and spread out, much like the waterways, you can imagine them just like point ripples. That diffraction causes it to spread out. Those waves overlap, and where they're overlapping, they're sometimes in phase, sometimes out of phase. So you get constructive and destructive interference. The cool thing about the light one is it makes this beautiful pattern of light and dark spaces, fringes we call them, on a screen if you make it do it, and that's very, very useful. We call these interference fringes, and we can actually work out the wavelength of that light using it actually. So you can imagine here, if we were to draw lines to these peak intensities, you'd see that these were areas, that entire line of action would be constructive. That entire line of action from that one would be constructive, but then these bits where the amplitude is nothing, we have a dark fringe around there. We should find that it would be a destructive line, a line where all of the wave fronts are cancelling each other out, just like the water. So a guy called Young observed this and made an equation for it. So it was called the Young's double slit experiment. He determined that there was a relationship between the slit separation, A, the wavelength of the light, lambda, the distance from the slits to the screen, D, and the width of the fringes, X. So through this, it could set A, D, and X and determine the wavelength of light. It took the form of that. Lambda equals AX over D. So that's a formula that you need to know, and well, you need to be able to use. You get given it in the formula book, so don't worry about that. But yes, this is Young's double slit formula. In order for this to happen, though, light needs to be coherent, and that means that constant phase difference is the strict statement here. So if 2 light sources are not coherent, yet they may interfere with each other, but in a spiky, non-consistent way. So they would interfere and then separate out, or interfere a little bit and separate out. They may get some local changes, but if they're not coherent, you won't observe these great constructive and destructive effects. So yeah, 2 waves are said to be coherent if the waves emitted from them are in phase, or if they have a constant phase difference. This implies that the sources have the same frequency and thus same wavelength, if they're the same type of wave in the same medium. Right, so imagine a laser shining through 2 slits like we've just seen there. The reason we'd use a laser is because laser light is monochromatic of 1 frequency, and all of the light coming from it is coherent, because of the way that lasers work. It's all coherent light. Now if we shine that laser light through 2 slits, that means that you've got 2 point coherent sources of light. So they're going to work perfectly to describe this process. So if you imagine light traveling from S1 to N, or S1 to L, and then from S2 to L, they're going to, when those two lines of action meet, if it's bright, then they've met and they were in phase when they hit. If they landed on a dark bit, then those two lines of action were out of phase. They were 180 degrees out of phase. Now sometimes we refer to that in terms of path difference. So the distance that one's travelled is a whole number of wavelengths, for example, and the distance the other one has travelled is a whole number plus a half wavelengths. And so they're out of phase or in phase. So we talk about path difference. If you've got 0 path difference, it's equatable to 0 phase difference. Or if you've got n integers of path difference, that's equivalent to 0 phase difference. So point L is a point where they're in phase, so they've got a path difference of either one wavelength or no wavelengths or an integer multiple of wavelengths. Point M, like we just said, is getting antiphase, so it's going to be half a wavelength out of cycle, so we're getting destructive interference. And point N, constructive, in phase again. So we can put it in terms of phase or path difference. So if you've got a path difference of n lambda, your waves are arriving in phase. That's the distance that your two waves have travelled. If it's different by a whole number of wavelengths, they're going to be in phase, which means you're going to get constructive interference. If the distance that the two waves have travelled to meet a single point, it has a path difference of n plus a half lambda, then they're going to be out of phase when they land, and you're going to get destructive interference. Right, sorry about that. So, you also have these things called diffraction gratings, which take advantage of the effect of diffraction by putting lots and lots and lots and lots of lines in place, often of the order 600 lines per millimetre. So you can imagine how tightly spaced they are. They're effectively scratched into this thin glass plate. And then each one of those lines will act as a point source of diffraction and can cause spreading out. So what you get here is different order maxima on a screen, or different orders where you're getting constructive interference. So if we just go back for a second and we look at this, now it'd be better to look at it. So each one of these lines, a C line, is a line of constructive interference. Now, with two waves, you don't get many, you get one or two. But with a diffraction grating, you're going to get loads, because they're so tightly packed together, all these diffraction gratings, you're going to get loads of points of interference. So each one of these orders is an order, what we call an order maximum. So first order maximum, second order maximum, the point at which you're getting constructive interference. Now, if we look at it like this, we can see that the difference that one light wave has travelled going, let's say, that side of the normal line is going to be, the very first order maximum is going to have a path difference of 1 lambda. So if it was straight ahead and they both travelled the same distance, they've both got a path difference of 0 lambda, and then I move it along, they're going to go from being fully in phase, slightly out, and then as soon as the difference in the distance they've travelled is 1 lambda, then they're back in phase again. Now, that little sticky out, that little extra bit there, if we imagine looking at that at the source, that equates to this little triangle here. This little extra bit here is the extra bit that this has travelled. If this is a perpendicular line, if this line of action here is a perpendicular to this line, then this little bit here is the extra bit that this has travelled. And if that's lambda, then they're in phase. So we can set up this triangle here where D is the slit separation, lambda is this extra little bit here, and this angle theta, we call it our diffraction angle. We call it our first order diffraction angle. So we can say that d sine theta is equal to lambda for theta.